Today we're going to learn some new concepts, which are conditional probability, marginal probability, law of total probability, Bayes theorem, and independent events. Okay, let's have a look at them one by one. So first of all, conditional probability. First, I'll introduce the concept and the definition. And next, I'll set you an example to illustrate this. Okay, by definition, given two events A and B, and the probability of B is more than zero, the conditional probability of A given B is defined as the quotient of the probability of the intersection of events A and B, and the probability of B, denoted as the probability of A given B is probability of A intersect with B divided by the probability of B. Or we can also write it in a product form, which means the probability of intersection of A and B equals the conditional probability of A given B times the probability of B. So note that this is read as the probability of A given B. Okay, this is a conditional probability, which means we know that B already happened. And under this situation, we calculate the probability of A. Understand? Okay, I'll show you an example. Example 1. Married couple has two children. A, what is the probability that at least one of the two children is a boy? B, given that we already know that one of them is a girl, what is the probability that at least one of them is a boy? Okay, so for the first question, what is the probability that at least one of the two children is a boy? So suppose we denote two events. Event A is at least one of the two children is a boy. So what is this event? The event contains three elements, right? It can be boy, 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 girl, and girl, boy, right? Okay, so what is a sample space? Sample space, if we have two children, we can have boy, girl, boy, boy, girl, boy, and girl, girl, right? There are four sample points in the sample space. So just for the first question, the probability of this event is the probability of is the number of sample points in this event over the number of sample points in the sample space, which is 3 over 4, right? So for the first question, the probability is 3 over 4. For the next question, we need to denote another event, right? Because here it says we have already know that one of them is a girl. So that means there is another event, at least one of the two children is a girl, right? And here we want to calculate the probability of A given B, right? That means we know that B already happened. At least one of the two children is a girl. This event has already been happening. And under this situation, we calculate the probability of A. That means the probability of A given B. So this is defined as the probability of intersection of A and B over the probability of B, right? Okay, so first of all, let's see what is B. B is at least one of them is a girl. So that means there are three sample points: girl, 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 boy, and boy, girl, right? Okay, so A intersection with B is a common part of events A and B, right? The common part is boy, girl, and girl, boy, right? So there are two elements in the intersection, and there are 4 elements in the sample space. Sorry, 2 over 4. And the probability of B has 3 sample points, right? Over sample space has 4 sample points. So this probability is 2 over 3. Did you see the difference? If there is no constraints, there is no condition, the probability of A is just 3 over 4. If we know that event B happened, the conditional probability of A given B is 2 over 3. That means given the additional information, we know that the probability of A given B is smaller than the original, right? So that means additional information can affect the probability of an event. Okay, any questions? Okay, and you can check this solution after the class. Next, example 2. Okay, suppose here we have 2 events. Event A is cause of complaint is appearance. Event B is complaint occurring during guarantee period. And we have a table here, lists all the distributions of product complaints. For some complaint, the complaint is because of electrical problem, or it can due to mechanical problem, or some because of the appearance problem. And we also know that some complaints happen during the guarantee period, and some complaints happen after the guarantee period, right? So this table lists all the distributions of product complaints. So here we want to find the probability of A given B. So how do we calculate this? Okay, by definition, the probability of A given B is defined as the probability of the intersection of A with B, right? Over the probability of B, right? Okay, so first of all, we need to check the probability of the intersection between A and B. Okay, A is cause of complaint is appearance. Event B is complaint occurred during the guarantee period. So what is the intersection? So appearance is here, and during the guarantee period is here. So the cross point here is the probability of the intersection, right? So this is 32%. Next, we need to check the probability of B. B means complaint occurred during the guarantee period. Complaint happened during the guarantee period. We need to use this probability, right? Because the total probability that it happened during the guarantee period is 63%, right? So the ratio between these two numbers is the conditional probability, which is approximately 0.51. Okay. Any questions? No? Okay, let's see another example. Okay. This table gives a classification of all employees of a company by gender and college degree. That means if we randomly chose an employee from this company, this employee can be a male, right? And it can also be a female. Also, the chosen employee can have college graduate certificate, or he or she is not a college graduate, right? So this table lists all the possibilities here. And if one of these employees is selected at random, the question is, what is the probability that this employee is a female, given that we know this employee is a college graduate? Okay. All right, I'll leave you 3 minutes to think about this question. Okay, I'll give you a hint. There are two events, right? First event is this employee is a female. Okay, we have another event G, denoting this employee is a college graduate. And here we want to find the probability of what? The probability of F given G, right? That means we have already know this employee is a graduate. Under this situation, we calculate the conditional probability of F given G, right? So what is the conditional What is the conditional probability of F given G? I'll leave you 3 minutes to think about it. Okay, any ideas? Okay, we calculate conditional probability by definition, right? Probability of F given G is defined as the probability of the intersection of these two events over the probability of event G, right? So first of all, let's calculate the probability of the intersection. Intersection means if you randomly choose an employee from this company, this employee is a female and is a college graduate. So how many people are there? There are 4 people, right? So 4 over the total number of people in the sample space, which is 40. So this is the probability of the intersection. Next, let's calculate the probability of this employee being a graduate. So how many college graduates are there? There are 11, right? So the probability of this employee is a graduate is 11 over the total number of employee. Okay, so this conditional probability is 4 over 11. All right, any questions? No? Okay, let's see the next one. Okay, next concept is called marginal probability. Marginal probability is relatively easy to understand. This is a simple probability. It's a relative concept compared to conditional probability. By intuition or intuitively, you can treat it as normal probability. Okay, I'll read the definition for you. Marginal probability is the probability of a single event without consideration of any other event. Marginal probability is also called simple probability. For example, if we have a table that is from the previous example, the marginal probability in the above diagram, probability of male is 27 over 40, right? Because you have total number of 27 male over the total number of employee, which is 40. And the probability of a randomly selected employee is a female is 13 over 40, right? Because we have 13 employees that are female. Also, if we calculate the probability of a randomly chosen employee is a college graduate, this is 11 over 40 because we have total number of 11 college graduates there. Also, if we calculate the probability of not a college graduate, we can simply use the number of not a college graduate, which is 29 over the total number of employees, which is 40, right? These four probabilities are called marginal probabilities because when we calculate them, we do not consider any other event, right? These are just simple probabilities. Okay, do you understand? Any questions? Okay, if you do not have any questions, let's do a quick quiz. Conditional probability and exercise. If I roll a fire die, let A be the event that the outcome is an odd number. That is, A is an event that contains 3 elements of 1, 3, 5, right? Also, let B be the event that the outcome is less than or equal to 3. That is, event B is defined as a set that contains 1, 2, 3. The question is, what is the probability of A? PA. What is the probability of A given B? Which means the probability of A given B. Okay, here we need to find 2 probabilities. Okay, I'll give you 5 minutes to think about this question. All right, any ideas? Okay, first of all, let's calculate the probability of A given no conditions. Okay, probability of A is defined as the number of sample points in this event over the number of sample points in the sample space, right? Okay, so first of all, what is a sample space? If I roll a fire die, sample space, of course, is 1, 2, 3, 4, 5, 6, right? Because there are 6 faces in a standard die. Okay, so the probability of event A is, so how many sample points in this event? There are 3 sample points over 6 sample points in the sample space. So the probability of this event is 1 over 2, right? Okay, next, let's calculate the probability of A given B. Okay, the probability of A given B is denoted as number of sample points, the probability of intersection of A with B, right? Over the probability of B. Okay, so what is A intersect with B? So first of all, let's find what elements are inside A intersect with B. So A is an element, A contains element 1, 3, 5, and B contains element 1, 2, 3. So the intersection between A and B is a set that contains 1 and 3, right? There are 2 sample points in the sample space over 6 sample points in the sample space. So this is the probability of intersection of A and B. And let's calculate the probability of B. B has 3 sample points over sample space has 3 sample points. So the denominator is the probability of event B. Okay, so let's simplify this and we can get 2 over 3. So this is a conditional probability of A given B. Okay, any questions? No? Okay, let's see the next concept. Next concept is called law of total probability. If B1 and B2 are 2 events in the sample space S, the intersection between B1 and B2 is empty, and the union of B1 and B2 is a whole set, which is sample space. And also, the probability of B1 is above 0, and the probability of B2 is also above 0. Then, for any event A in the sample space, we can have the following formula, which means the probability of A can be divided into 2 parts. First part is the probability of B1 times the probability of A given B1, plus the second part, which is the probability of B2 times the probability of A given B2. Okay, this can be also illustrated in the following Venn diagram. So first of all, we have a sample space S, right? Okay, suppose this is sample space S, and note that we have defined 2 events in the sample space. First one is the left-hand side B1, and also the right-hand side B2. And also we know that there is no common part between B1 and B2. And also B1 union B2 is S. So that means B1 is complementary of B2, or B2 is complementary of B1, right? Okay, so now we have another event A. A is also in the sample space. So the probability of event A is divided into 2 parts, right? First part is A intersect with B1. Next part is A intersect with B2. So the probability of event A can be divided into 2 parts, right? First part is if B1 happens, we use probability of B1 times the probability of A given B1. This is actually the probability of A intersect with B1, right? And the second part is the probability if B happens, we use probability of B2 times the probability of A given B2, right? According to the definition of conditional probability, this is actually the probability of A intersect with B2, right? Okay, so do you have any questions? Any questions? Okay, please write down this formula on your notebook, okay? Because we're gonna use it to solve some example questions later. Done? Okay, so note that B1 and B2 are complementary with each other, right? So we can also write it as B or B prime. So the law of total probability can also be expressed as this formula. Please also write down this formula. This is actually the same thing compared to the previous formula, right? Basically, it means the probability of A has two parts. The first part is if B happened, we use probability of B times the probability of A given B. Also, it has second part. Second part is if B prime happens, we use the probability of B prime times the probability of A given B prime. Okay, please write this down on your notebook. We're gonna use it to solve some questions. Okay, let's see some concrete examples to help you understand. Suppose there are only two factories supplying light bulbs to the market. Factory X bulbs work for over 5,000 hours in 99% of cases, whereas Factory Y's bulbs work for over 5,000 hours in 95% of cases. It's known that Factory X supplies 6% of the total bulbs in the market, and Y supplies 40% of the total bulbs in the market. What is the probability that a purchased bulb in the market will work for longer than 5,000 hours? So how do we approach this problem? Okay, so if we have a randomly selected bulb, if the bulb is all from factory X, so what is the probability that it will work for longer than 5,000 hours? So in that case, it must be 99%, right? Because if all the bulbs from factory X, so that means all the bulbs can have a 99% probability that can work for over 5,000 hours, right? Otherwise, suppose all the bulbs are from factory Y. In that case, the probability that this bulb will work for longer than 5,000 hours must be 95%, right? But note that in the market, there are bulbs from X and there are bulbs from Y, right? So if you randomly choose a bulb, the probability of this bulb will work longer than 5,000 hours should lie between these two values, right? Because some of them are from X and some of them from Y. So intuitively, the probability should lie between these two values, right? Okay, the task is what exactly the value is. Okay, so here we can use a total probability law. Okay, there are 3 events. One of the event is this bulb will work for longer than 5,000 hours, right? We want to calculate the probability of this event. So this event is the most important one, right? Also, we have another event called B1, which means this bulb was supplied by factory X, right? And we have another event is this bulb was supplied by factory Y, right? And we also know that B1 intersect B2 is empty set, right? Because the bulb cannot be supplied both by X and Y. We also know that B1 union with B2 is a sample space because there are only 2 factories supplied light bulbs to the market. This is assumption, right? Okay, so here we want to find the probability of event A. According to the total probability law, this probability has 2 parts. If B1 happens, it is the probability of B1 times the probability of A given B1, right? And if B2 happens, this is probability of B2 times the probability of A given B2, right? This probability comprises of 2 parts. Okay, so that means let's see, what is the probability of B1? The probability of B1 means the probability of this bulb was supplied by factory X. Okay, so this number is here, right? Because it says X supplies 60% of total bulbs in the market. So if you randomly choose a bulb from this market, the probability of this bulb was supplied by factory X is 60%. Next, the conditional probability of A given B1 means if this bulb is from B1, if the bulb is from factory X, the probability of this bulb can work for longer than 5,000 hours, right? This is the meaning of this conditional probability. And this number is 99%. Why? Because it says here, if the bulb is from X, factory X bulbs work for over 5,000 hours in 99% of cases. So this number is 99. Okay, so how about the second part? The probability of B2 means the probability of this bulb was supplied by factory Y. This number is here because it says Y supplies 30%. So let's put 40% here. Next, the probability of A given B2 means if this bulb was supplied by factory Y, what is the probability of this bulb can work longer than 5,000 hours? And this number is shown here. This is 95%, right? Okay, so if we add these 2 numbers up, we can find this number is actually 0.974. So this is a probability of a randomly chosen bulb can work for longer than 5,000 hours. Understand? It's something, it's sort of like a weighted average. It's from the law of total probability. Okay, any questions? No? All right, let's see another example. This time, I'll give you 5 minutes to think about this and solve it by yourself, okay? Assume in the class 80% of the students do their homework and 20% do not. And if a student does his or her homework, the probability of him or her passing the final exam is 90%, whereas if one does not do his or her homework, the probability of him or her passing the final exam is 10%. If we randomly choose a student from this class, what is the probability of him or her passing the final exam? Okay, I'll leave you 5 minutes to think about this. Okay, have you finished? How do we solve this? What is event A? Event A is this student passes the final exam, right? So let's say this student passes exam. And what is B1? B1 is this student does his or her homework. This student does his or her homework, right? And event 2 is this student does not do his or her homework, right? And we also know that B1 intersect with B2 is empty set because there is no common part between these two events. And also we know there are only two types of students. So B1 union with B2 is the universal set, which is sample space. So according to the law of total probability, probability of event A is the probability of B1 times the probability of A given B1, right? Plus the probability of B2 times the probability of B1 given B2 happens, right? Okay, so what is the probability of B1? Probability of B1 is probability of a randomly chosen student does his or her homework. So this is 0.8 because it says here 80% of the students do their homework. Okay, times if the student does his homework, the probability of him or her passing the exam, right? So it says here 90%. So times 0.9 plus the second part, which is the probability of this student does not do his homework, which is 0.2 times if the student does not do his homework, the probability of him or her passing the final exam, which is 10% only, right? So times 0.1. Final result is 0.74. This is a probability of the event A. Okay, any questions? No? Okay, if you're interested, you can check the solution after the class on the next page. All right, next, we're gonna introduce Bayes' theorem. Okay, first of all, I'll read the concept for you, okay? And after that, I'll set you an example to illustrate what does this mean. So the Bayes theorem tells us the probability of A given B is the ratio between two parts. The numerator is the probability of A times the probability of B given A. The denominator is probability of B. Why? Because according to the conditional probability, the probability of A given B is actually the probability of A intersect with B over the probability of B, right? And also we know that the probability of A intersect with B can be rewritten as the probability of A times the probability of B given A. This is by definition of the conditional probability, right? Remember, there's a product form of the conditional probability. So this is the first part. So next, we can further expand this conditional probability to this form. So the numerator does not change. The denominator can be rewritten as a total probability. That means the probability B can be rewritten as two parts. First part is probability of A times the probability of B given A, plus the second part, which is the probability of A prime times the probability of B given A prime. Okay, so let's write this down on our notebook. We're going to use this theorem to solve some questions. Of course, there are some conditions when you use this formula. First of all, A and B are events, and probability of B is not 0 because probability of B is the denominator. Denominator cannot be 0. And also, the probability of A given B is a conditional probability. The likelihood of event A occurring given that B is true. This is by definition, right? Next, the probability of B given A is also a conditional probability. That means the likelihood of event B occurring given that A is true. Okay, next, probability the probability of A and the probability of B are the probabilities of observing A and B independently of each other. This is known as marginal probability. Okay. First of all, let's write this down on your notebook, and next we'll see some concrete examples. Okay, I'll leave you 1 minute. Please write this down. Okay, finished. Next, let's see an example first. Assume on a summer sunny day, the probability you see a dangerous fire is 1%, and the probability you see a smoke is 10%. That's probably due to common barbecue activities in summer. Also, we know that 90% of dangerous fires make smoke. The question is, when you see a smoke, what is the probability that there's a dangerous fire? Okay, so how do we solve this? We want to know the probability of there is a dangerous fire, right? And given the condition that you see a smoke. So let's first denote these two events with two letters. Okay, event A is the probability of what we are concerning, right? So event A is there is a dangerous fire. Okay, so what is event B? Event B is you see a smoke. Right? Okay, so here, according to the question, we want to find a conditional probability, which is a conditional probability of A given B. That means when you see a smoke, event B happens, the probability of A given B, right? Okay, so according to Bayes' theorem, first we can expand this conditional probability to this one. The probability of A times the probability of B given A, right? And for the denominator, it's simply probability of B. Now let's check, do we have all the numbers we need? First of all, what is the probability of A? Probability of A means the probability of there is a dangerous fire. Okay, it says here the probability you see a dangerous fire is only 1%. So let's put 1% here. This is the probability of there is a dangerous fire. Next, let's check the second conditional probability. This means conditional probability of B given A, which is given that there is a dangerous fire, the probability of it makes smoke. So according to the question, this probability is 10% because it says here, sorry, it's not 10%, it's 90%, right? Because it says 90% of dangerous fires make smoke. That means if there is a dangerous fire, the probability of it making smoke is 90%. So let's put 90% here. And for the denominator, this is the probability of B. That means in the summer, the probability of you see a smoke. And this probability is 10%. It's because it says here, the probability you see a smoke is 10%, right? So here we got all the numbers we need. So we do not need to expand it a little further. So after calculation, this probability is 9%. That means the probability of there is dangerous fire given you see a smoke is 9%. Right? Okay, have a look at this. Any questions? No? All right, let's see another one. Assume in a city 0.04% of all citizens have a certain type of cancer. Also, we can use a machine to test the cancer. However, the machine is not always correct. If a person has this cancer, the test result from this machine shows that the probability of this person having this cancer is 99%. Okay, pay attention to all the numbers here. If a person does not have this cancer, the test result of this machine shows that the probability of this person not having this cancer is 99.9%. Okay, so what does this mean? This means the machine is not always correct, right? So now if we randomly select a person from this city and use this machine to give him a test, and the test result shows that this person has this cancer, what is the probability of him having this cancer? So the question is, if the test result is positive, does that mean the person must have this cancer? Of course not, right? Because the machine is not always correct. So based on the past information, we can calculate this conditional probability. Why is the conditional probability? Because it's probability of him having this cancer, given that we know that test result is positive, right? So what are the two events here? Think about this. What are the two events here? Okay, so what is event A? Event A is the event we are really interested in, right? So event A is this person has cancer, has this cancer. Okay, so what is event B? Event B is a conditional event, right? What is the condition here? Condition is the test result of this person by this machine is positive. So let's say event B is test result of this person by this machine is positive. Okay, so if we have these two events, we want to calculate the probability, conditional probability of A given B, right? That means given that test result is positive, the probability of A. Okay, according to Bayes' theorem, this can be expanded to probability of A times the probability of B given A over the probability of B, right? So first of all, let's check, do we have all the numbers we need? First of all, the probability of event A, this person has this cancer. We have this number, right? This number is 0.04% because this person is from this city. So in the city, the probability of this person having this cancer is only 0.04%, right? So the first probability we have. Next one, the probability of B given A. That means if the person has this cancer, the probability of test result is positive given this person has this cancer. So it says here 99%, right? Because it says if the person has this cancer, the probability shows the person having this cancer is 99%. So for the numerator, we have all the numbers we need. How about the denominator? Denominator is the probability of test result of this person by this machine is positive. Of course, we do not know this probability directly, right? So we need to further expand the denominator into two parts. The first part is the same as the numerator, which is PA times PB given A, right? Second part is PA prime times PB given A prime happens, right? Okay, so let's check if we have all the numbers. The first part, of course, we have all the numbers we need because it's the same as the numerator. Second part, PA prime is simply the opposite of PA. Of course, we have this number. Next, if the person does not have this cancer, the conditional probability of the test result is positive. Also, we have this number, right? So let's put all the numbers in. First of all, probability of A is 0.04% times probability of B given A. This is 99%. Just copy from the question. Okay, for the denominator, the first part is the same as the numerator, so just copy them down. Next part, the probability of A prime, that means 1 minus 0.04%, right? Second part is if the person does not have this cancer, the probability of giving a positive, this is 1 minus 1 minus 99.9%, right? Okay, so we have all the numbers we need, and we can calculate final result, which is 0.284. So this is the conditional probability we are looking for. Okay, any questions? No? All right, you can also check the solution for these questions after the class on the next page. Okay, next we'll do a quick quiz regarding the Bayes theorem. So this time I'll give you 5 minutes to solve it by yourself, okay? In this question, there are 2 identical plates containing some candies as shown on the left. For the first plate, there are 30 fruit candies and 10 chocolate candies. For the second plate, there are 20 fruit candies and 20 chocolate candies. So suppose here you close your eyes and randomly select a plate. This is the first step. Imagine that if you close your eyes, randomly select a plate, then randomly select the candy from the chosen plate. Then you open your eyes and you find that the candy you chose is a fruit. And given this information, the question is, what is the probability that plate number 1 is chosen? So I'll give you a hint. So intuitively, when you find your chosen candy is a fruit, which plate is more likely to be chosen? Do you understand? Okay, so when you find the candy you chose is a fruit candy, which plate is more likely to be chosen? Of course, it seems like to be the first one, right? Because in the first plate, the percentage, the probability of choosing a fruit candy is more than the second plate, right? So what exactly is that probability? Now we need to find the exact probability of plate number one is chosen. Okay. And also, if you don't have the given information, what is the probability of choosing plate number one? If you don't have this information, of course, it is 50%, right? Because if you randomly chose the plate, there are 50-50 chance you draw plate number one, right? But here we know all the given information here. This is the given information. That means you have some additional information to help you to decide the probability of plate number one is chosen. So how do we calculate that probability? Okay, think about this. I'll give you 5 minutes to solve this by yourself. Okay, have you finished? All right, we have to define two events, right? First event is event of interest. That means the plate number 1 is chosen. So how about event 2? Event B. Event B is the event that already happened, right? Event B is the chosen candy is fruit. So here we want to find the probability of A given B, right? That means given that the chosen candy is a fruit, we want to find the probability of A given B. Okay, according to Bayes' theorem, we can expand this to the right-hand side, right? Okay, let's check if we have all the numbers. First of all, PA. PA is the probability of plate number 1 is chosen, given no conditions. Of course, this is 50%, right? So first one is known. Next, given the first one is chosen, the probability of B given A. Of course, this is also known, right? This is 30/40. Okay, how about the denominator? Denominator is a probability of the chosen candy is a fruit. This is not known because it depends on which plate is chosen, right? So this is not directly known. So we need to further expand this into two parts. Okay, first part is the same as our numerator. Okay, second part is probability of A prime plus times the probability of B given A prime, right? Okay, so now let's put all the numbers in. As we said, probability of A is 0.5 and probability of B given A is 0.75. Okay, for the denominator, first part is the same as numerator. Second part, first of all, the probability of A prime, that means the probability of choosing plate 2, which is also 50%, right? Next, if we choose plate number 2, the probability of choosing a fruit candy given plate number 2 is chosen is 50%, right? Because 20 fruit, 20 chocolate. So there's a 50% you choose a fruit. Okay, so after calculation, the probability is 0.6. Okay, do you understand? That tells us, given the additional information, we know that the probability of choosing plate number 1 is slightly higher than 50%, right? So these extra information did help us to make a decision which is more accurate. All right, any questions regarding the Bayes theorem? No? Okay, let's see the next concept. And this is the last concept we're gonna learn in today's lesson, which is called independent events. Okay, first of all, I'll read the definition for you. In probability theory, two events are said to be independent or statistically independent if the occurrence of one does not affect the probability of occurrence of the other. Okay, there are two examples. First of all, if you toss a coin and it comes up heads 3 times, what is the chance that the next toss will also be a head? The chance is simply 0.5, just like any toss of the coin, right? So this means what it did in the past will not affect the current toss. So this is an independent event. So another example is taking colored marbles from a bag. As you take each marble, there are less marbles left in the bag. So the probability change, right? For example, originally we can have two white balls, two white marbles, and two black marbles. After the first pick, suppose we pick a black marble. What's left there is two white marbles and one black marbles. So in the original situation, the probability of choosing a white marble is 50%, right? After the first pick, the probability of choosing the white marble becomes 2 out of 3, right? So this situation does not look the same, right? So that means this event is not independent. The decision in the first pick affects the probability in the second pick. So these events are not independent. So this is called dependent events. Okay. Okay. So next, how can we decide the two events are independent or not? We can use this conclusion. So I'm not gonna prove this for you here. You can just remember this conclusion and use them to prove if the two events are independent. So basically, if two events A and B are independent, this statement is equivalent to the following three statements. So that means A and B are independent is equivalent to PA equals PA given B, or PB equals PB given A, or the probability of the intersection between A and B equals the probability of A times the probability of B. We use the third statement more often. So next time, if you want to prove or if you want to decide the two events are independent or not, the only thing you need to check is if the left-hand side is equal to the right-hand side, okay? Okay, let's see an example. Okay, we have seen this example in our previous slides, right? So all the conditions are the same with our previous example. And the question changes. Question is now, are event A and B independent events? Event A is cause of complaint is appearance, and event B is complaint occurred during the guarantee period. Question is now, are event A and B independent events? Okay, remember that if you want to decide if the two events are independent, you need to check if the probability of intersection of A and B equals probability of A times probability of B, right? Okay, so I'll leave you 5 minutes to think about this question. Okay, have you finished? All right, first of all, let's calculate PA first, okay? PA is probability of this cause is appearance. So according to the table, the number is here, right? 30%, 35%. Next, the probability of B. This number is here. The complaint happens during the guarantee period, which is 63%, right? So the probability of A times probability of B is 35% times 63%, which is approximately 0.2205, right? Okay, next let's calculate the left-hand side. Left-hand side is the probability of A intersect with B. That means the cross position of cause of complaint is appearance. This is this column. B is complaint occurred during guarantee period. So this row, the number is here, right? 32%. So of course, the left-hand side does not equal the right-hand side. So because left-hand side does not equal right-hand side, you can say that A and B are not independent. Okay, any questions? Okay, if you don't have any questions, the remaining time is for you to complete today's homework. Remember to submit it before the deadline, okay?